The goal of this tutorial is to present the use of GNU Radio on embedded hardware with an operating system built by BuiltFruit. This tutorial is split into three steps. First one is a presentation of BuiltFruit and a comparison with some distribution like Debian or Ubuntu. After that, we will download a BuiltFruit source and to configure and build this. And finally, we create two flow graphs. The first one is executed on a target board and contain a signal source and the 0MQ publisher. The second is on the PC side with 0MQ subscriber and a plot to display the signal received from the target. So, what is BuiltFruit? BuiltFruit is a build system. This type of tool is used to build a full operating system. This means, and the first task is to have access to a compiler. Usually, when the host computer is based on an Intel processor and the target has a different architecture, it's a cross compiler. This tool is dedicated to be executed on the host computer, but to produce binaries targeted for the embedded platform or in different architecture, ARM, PowerPC, RISC-V, etc. The second task is to build a bootloader. Bootloader is quite equivalent to a BIOS, and the kernel to deal with hardware access. The next task is to populate the root file system with libraries and applications selected by the user. And at the end of the build, it produces a disk image. This file is used to write SD card or SPI flash or an eMMC or a drive, of course. The interest of this approach is to have small disk space and small build time. Small disk space in host because only the selected tools and library are built, not everything. And by selecting some option or sub-option, it's possible to reduce or to really target a specific application and small build time for the same aspect. In a specific case of BuiltFruit, the resulting image disk is a firmware. This means it's not possible to modify or to update, install, uninstall application or library in live. If something must be modified, you need to go back to BuiltFruit to update the configuration, to build again, and to flash again. But why using BuiltFruit? It's true. Modern distribution like Debian or Ubuntu may be used with for different architecture, Intel architecture or ARM, PowerPC or RISC-V. The good aspect of binary distribution is the easy to use. You install an application, everything, all required dependencies are automatically installed by the package manager. And it's fast because everything is already built. You fetch binaries and you don't lose time with the build, with the configuration of each libraries or application. But it's not targeted for a specific CPU or specific version of an architecture. No, it's targeted on global processor. For example, all ARM, or all PowerPC or all RIS file. So it's not possible to take advantage of a specific instruction for the latest generation of Intel processor, for example. The second drawback with this approach, the maintainer decide which options are set or unset, and consequently, if the maintainer decide to enable everything, the final binaries is high, and this increases the storage space. At the opposite, BuiltFruit and the firmware produced by BuiltFruit is tailored for the specific architecture. It's not generic ARM, but it's specifically for a version of ARM, for example, Cortex A9, and consequently, every instruction are available. The second aspect, it's tailored for an application or for goal. You need an embedded board for a specific task. You select every package required, not rest, and you have something really optimized for this task. But since every package must be built, it takes time, big time compared to a binary distribution, and it's not possible to update in live your system. You need to rebuild after having modified, updated your configuration. But to compare a bit this two approach, BuiltFruit with GNURadio may be used with a Pluto SDR and fit the SPI flash. It's small, but this space is enough to support BuiltFruit, GNURadio, Python. Volk with Raspbian can't be used, optimized, and floating point unit available on processor, on ARM processor, on Broadcom processor, because this distribution may be used for Raspberry Pi 1, 2, 3, 4, and consequently is 52 bits. Neuron may be used with BuiltFruit with a better performance, around 6 times better than a generic implementation. Okay, we have seen basic, so we more closely to BuiltFruit structure. The tree or the directory of BuiltFruit look like this. There are more directories than that, but it's most important directories. The first one, configs, contain the bare minimal configuration. Each configuration address one board. There is a configuration for the Raspberry Pi 1, Pi 2, 3, 4, BeagleBone, BeagleBone Black, Beagle 5, etc. By bare minimal, I mean it's the strict required set of application and information to be able to build a system and to have a bootable image. The model of the CPU is provided, the version of the bootloader, the version of the kernel, but there is really no application. There is no SSH server, no client, etc. The second important directory is package. Package contain a big 2,000 subdirectories. Each of them contain recipes to build an application of library. Provide the relationship between an application or library and other application or other package, to be short. where to download, how to configure, how to patch, and how to build the corresponding package. The last one is output. Output is working directory, the BuiltFruit working directory with some important subdirectories. The first one is the host. It contains all tools able to be used by the host computer to do something with target. It contains the cross compiler. It contains, for example, if QEMU, an emulator is set, it contains QEMU, etc. Every tool used by the host computer. Build directory is the location or where all packages are extracted, built, configured, built, and not the last. The target directory contains it's the image of the future image disk. This is here. All packages are installed after the build step. And finally, the output image is the final image location. In this directory are installed the bootloader binary, the kernel binary, and the root file system partition, and finally the image where everything is provided to flash an SD card. The official BuiltFruit provides plenty of config, plenty of package, but it's possible to extend. The bar minimal configuration are sometimes boring because you need to configure each time you start with a new BuiltFruit which package you want. It's possible to create a custom dev config, but it's not a good idea to move, copy this each time in the BuiltFruit directory. Better approach is to use a BR2 external. This is maybe seen as a lawyer to extend BuiltFruit by configuration, by new package. There is two examples. The first one, Pluto SDR, is focused on Pluto SDR and provide every tool needed to use this. Is same approach. It's the same target ID to the official analog devices repository, but in more easy to maintain. The second one, OSKIMP BR2 external, is a most generic external with Raspberry Pi 3 and 4 configuration with GNURadio already set, and some new package like GNSS SDR. One important thing with to finish with the aspect of BuiltFruit is first I've talked about the relationship. There is two types of dependencies between packages. The first is the select. It's most easy to understand because a package, for example, some module of GNURadio depends of the FFTW library. This library has no many dependencies or many limitations. For example, not compatible with some compiler or something like this. So some package GNURadio modules may use select to automatically set this library without any manual intervention. At the opposite, there is depend on. The user has to manually enable dependency. It's, for example, again with GNURadio, Python 3 needs to be, or Python needs to be explicitly enabled by the user. Because first, it's possible to use Python 2 or Python 3, so it's not possible for BuiltFruit to decide which version to use. And Python has many dependencies, many limitations, etc. And consequently, it's to the user to select everything to fit, to match dependencies, to be able to use this interpreter. The second issue, maybe, with dependent is if all depend on for a package are not satisfied, the package is not shown. So it's difficult to see if the package is possibly usable or just absent to BuiltFruit. The second important thing is the pitfall. The first one is a classic pitfall with the modification, the update of the option for a package. If the package has already been built, if you select enable some sub option, and you just use make or rebuild the image, the package will not be updated, rebuilt, reconfigured, and rebuilt. You need to explicitly use the reconfigure and make. The second thing is the toolchain modification. In all cases, it's required to use make clean to suppress everything and to do make again. A toolchain modification is, for example, when you change the C library or you enable the C++ compiler or something like this. Last one is when you select a package with select for another for a dependency. It's required, it's better to check if this package is if this a sub option of a package or a new package, because it's a sub option is the same problem as second point. An important thing to flash your SD card. The most common command is dd with a source, usually the SD card.img provided by BuiltFruit, and destination. The destination is usually a SD card, but it's really important to double check if the /dev/something point of your SD card of your hard drive. This command will bit-to-bit overwrite the mass storage, and consequently it's not possible or really difficult to recover data lost, or simply the partition. Okay, we have seen basic of BuiltFruit. Now we will see modification needed on BuiltFruit to have access to GNURadio. First thing is about the toolchain. By default, BuiltFruit provides the uclipse, a C library, light C library, with some lack of support of not fully supported specification. Consequently, it's required to change this option to use the glibc, a more complete version. Usually, this is the version used by all distribution. Since GNURadio is written in C++, the C++ compiler needs to be set. Last thing is when to move file through the host computer and your target. One way is to use a SSH connection with a SSH server, SSH client, and SCP. So we need to set drop bear, lightweight version of SSH client server, and to be able to use SSH, the user by default root must have a password not provided by default. So it's important in the system configuration to provide a root password, for example, root. Last thing, again, with the idea of depend on, Python 3 must be set to have access to Python support. And finally, miscellaneous need to, in MISC, you need to set GNURadio, block support, Python, analog, and 0MQ to have access to all required blocks for this demonstration. And finally, devconfig provide a really small size partition, and it's not enough to with Python 3 and GNURadio, so it's mandatory to increase the size for something with better to fit requirement. After the theory, now it's time to do a bit of practice by playing with BuiltRoot. But first of all, we need to download an archive of BuiltRoot to the website buildroot.org. This provides some interesting things like documentation, but now it's download. We use the latest stable release. The file is quite small, and now we have this one somewhere. To extract, you need to use tar-xvf, extract verbose the file name, and to move to the directory by using cd BuiltRoot. The content of the directory look like quite the scheme presented earlier, and now you need to apply the default configuration. There is around 260 different dev config to allow for everyone to do some tests without real hardware. We use make. All commands start by make with BuiltRoot, and we use QEMU, an emulator for ARM processor. This devconfig provide set QEMU, so there is no need to install this package by using the package manager of your distribution. So just doing this. Now default configuration is applied. It's time to open the config panel by using make menu config. Enter. So it's curse interface. So to move between menu or option, you can use up and down key, page up, page down, or simply using key or the letter in blue in the menu. For example, first and to move in subdirectory, you point the subdirectory and you use enter. Here we need to switch the C library by using glibc. Again, we need the C++ compiler. To move to up in upper directory, first we need to use tab to switch to option at the bottom of the screen by using Tab. This allows to move, to exit, and using Enter. Second, system configuration, to configure the root password. Again, Enter to select, for example, root. OK, Enter. Again, exit. Now we need to select all required package in target package. One useful command to move quickly to a specific package is to use slash to have a search menu. And for example, for Raspbian, use search this. There is potentially many options. Here it's the first, and near all options there is a number. Just choose corresponding number to go directly to this option. Here it's okay for that. Now we need to enable a Python free interpreter. It's located in the interpreter subdirectory. Again, Enter. Move to Python. Select by using space bar and up to the upper level. An interesting thing again with GNURadio, specifically for Python, for example, is information explained earlier with dependent and select. Select, so everything is automatically will be set if this option is set, and it depends on this one. So this it's a logical or and etc. And for example, here we need to have the higher level package GNURadio set to be able to have this option displayed. Here in MISC, GNURadio, there is no other option displayed. If we enable this, we have everything. So you need blocks, you need Python to execute scripts, the run queues to transmit a stream, and analog. Here it's an example of select. Analog use FFT and filter, so these two options are set, and the dash explain it's not possible to disable these options. So exit, we are upper level, so the configuration panel asks you to save or not your modification. Yes, of course. It's possible when you are happy with your configuration and you want to save this to reuse more than one time. It's possible to use make again, save, def config. This will overwrite the default def config used. It takes a bit of time. If you read GNU def config, and you see GNURadio is set. Raspbian true. The root password is set. So this the def config has been updated with your specific needs. So now it's time just to type make to build everything, cross-compiler, file system, etc. And finally, to have access to binaries, file, ready to be used with, so to flash a card or to use with the QEMU. So now make. Okay. It's time for a coffee time because this take a bit of time because everything needs to be fetched, to be extracted, compiled, etc. So it's some common use. So you need to download this. You need to extract using tar, to apply a bar minimal configuration by using defconfig bar minimal or your custom configuration, to select package by using make menu config to have access to the configuration panel. The build is done by make, and if you have a real target board, it's possible to flash an SD card by using sudo to have super user write dd. If is the source, here it's SD card.img, and destination by using off /dev/ something. Take care to the destination. Again, it's if you use the wrong SD something, it's possible to lost content of a hard drive. There is some tips. First is for this time we have just to use one BuiltFruit, so it's okay. It's the first time, so all files must be downloaded. But it's useful if you have more than one BuiltFruit and to gain a bit of time by not downloaded again the archive, to use br2dld to specify a path somewhere where everything will be downloaded instead of in the DLD in the BuiltFruit directory. It's a good option. The second thing is to use br2cch in menu config. This allows to reuse some already built part of file. The C file is compiled in an object file, and the cch allows to store some parts of this process and reuse this to gain a bit of time again. To avoid to lose too many time, if you want to start quickly, it's possible to download all file required for the next step in at this address. So after a delay, depending on your host computer CPU and your internet connection, the BuiltFruit task is done, and now you have this message, and everything is okay. Before starting the new system through emulator, we will see a bit to the output directory filled by BuiltFruit. So we have build, host, image, target. Staging is a specific directory with libraries targeted for the embedded system. First, we have the host with all tools for your CPU, for your PC, to deal with the system, to build something with cross compiler, C++, C compiler, etc. You have some, for example, automake, everything required, and you have an emulator dedicated for ARM processor. Second directory is a built directory with everything built by BuiltFruit. So everything with the host is for the host, of course. You have FFTW required by GNURadio, some C library, GNURadio, etc. Everything selected using the menu config. Target is the future root file system. And finally, image, where are stored all binaries for your target, with the kernel image, the root file system partition, it's just a link, and a script with a basic functionality to boot the new system, with the emulator and some information, but it's not enough to be able to use our system and to use 0MQ subscriber and publisher. So again, binaries. This one is a complete line required to use the emulator or system for the specific goal. We have the emulators in just earlier, the machine type, the target CPU. We don't want to have a graphic interface, just one CPU, the path to the kernel image, command line to say where the root file system and which console, which terminal to use. But the most important thing, the rest is less important. Most important thing is the internet connection is used by user mode. This is the name of the interface, and since this emulator in this mode acts as a proxy between the host and the guest, we need to forward all ports required for this demonstration. The first one, this is the guest port, it's the host port. Maybe different or the same. For this, the 22 port is the SSH connection. But since it's possible to have an SSH server running on the host computer to avoid some conflict, we map this guest port to another port with an I number to allow the user to create this one. The second port is a port used by 0MQ. It's not required to have exactly this one, but we have selected this. And we forward the guest port to the host port with the same value. So now, if we use this and start this in a terminal or new system, boot, we see a DHCP client working with the proxy and the interface provided by the emulator. The SSH connection are started, so we need to use as login root, password root, or something you have used for in the menu config, and we have a prompt with nothing. But if we see this one is architecture, so it's match. this one is show it's a BuiltFruit built this day and for ARM64 processor. So this prove we use the correct system. To use the raw MQ for the publisher in a target side, we need to use the public address of the interface. To know this one, we use the ifconfig command to show the local interface, not shown at the outer the system, and the public interface and the public address. This one must be used when in a flow graph in a GNURadio. Now it's time to start with the GNURadio flow graph. The GNURadio demo will show this. Two flow graph. First one on your target side with a signal source to have a fake acquisition device, but instead of processing the data stream in the board, everything will send through the raw MQ to your CPU or your host CPU, to just in this case using a Qt sync to display the signal source. For both flow graph, GNURadio will be used. The first flow graph will be exported in the Python file, and this file sent to your target to be executed using the command line interface. The second one may be executed using the command line on your computer or by executing through GNURadio companion. So first we need to start GNURadio companion, of course. First, for the target flow graph option ID, we need a valid ID to comply. The generate option by default is configured to use a Qt GUI. So our board or emulator on BuiltFruit has no support for this one in this current configuration. So we need no GUI to just have a command line interface. It's all for options. We need a signal source. For this specific demonstration, we left unchanged. We don't have hardware to have a real sample rate, so we need to use a throttle. And we need a 0MQ publisher sync to send stream to the computer. This block must be configured by using again the public address of the board using TCP address port. This one used in the emulator configuration. And it's all. Save this flow graph, and we generate the corresponding Python file. This file may be sent to the board using SCP, secure copy, using network. Since it's not, we use a custom port instead of the official 22, we need to use the dash IP to provide the address, login arrobas, and it's a bit hard, but we need to provide the local address because QEMU act as a proxy. And finally, the directory where to store this file. For example, /tmp. Sorry, most important, the Python script. And it failed. It's not an error. It's just to explain. If you have already used your BuiltFruit or something in localhost with this IP, the key generated by the SSH server at the first boot is stored in a specific file. But if you build again your file, you lost this key, and SSH server will automatically generate a new one. And there is a mismatch between the stored previous key and the new key, and it's maybe a man-in-the-middle attack, or maybe just the key has changed. So SSH is friendly and provide the command to suppress previous key. It just requires to execute this command and to try again. This host is no more known, so we need to accept the new key, and you provide password. If go back to the target, cd/tmp, and the script is now available on your target. So now, second photograph for your computer, PC demo, for example. This time we need to use a Qt sync, yes. So we left generate option with the default value. This time we use subscriber source, and again TCP, but as for SSH, we use the local address, and again support. No hardware, throttle, and Qt sync. Save, of course. This time it's possible to use directly this new one. Not required. So okay, nothing. We see nothing because the script is not ready. We launch by using /script name. So the radio demo will show this two flow graphs. First one on your target side with a signal source to have a fake acquisition device, but instead of processing the data stream in the board, everything will send through 0MQ to your CPU or your host CPU, to just in this case using a Qt sync to display the signal source. For both flow graph, GNURadio will be used. The first flow graph will be exported in the Python file, and this file sent to your target to be executed using the command line interface. The second one may be executed using the command line on your computer or by executing through GNURadio companion. So first task is to start GNURadio companion. Okay. For target board, first BRGMO, for example, anything, it's not important. Since this flow graph will be used through the command line interface, we don't want a cute GUI, so we change the generate option. You need first signal source. Since there is no hardware device to fix the sample rate, you need a throttle, and we need a cute sync, for example this one. It's possible to left. Ok. On va couper ça après. So first thing is to provide an ID required. This flow graph is used in command line. We don't want to use Qt interface. It's okay. So first thing, is to start GNURadio companion. And for the first flow graph for your board, you need to provide a valid ID, of course. Since it will be used with in a command line interface, we don't want to use Qt. So now we need the signal source. There is no hardware to provide a real sample rate. We need a throttle, like this one, and we need a 0MQ publisher sync, this one. Now we need to configure this block by using this IP, using TCP, this IP port already used. Ok, c'est super, merci. And after a bit of time, because it's the first time GNURadio is used, some file, and we see the signal and the frequency match the 1 kHz frequency configured here. So this proves we are able to use GNURadio using a target and embedded board or an emulator to test or to demonstrate some concept without having access to the hardware. So now we have seen how to use GNURadio with basic demonstration, but this use quite nothing in the functionalities and capabilities of the CPU, and finally, modern board have plenty of resources, multi-core. Raspberry Pi has 4 core up to 1.5 gigahertz. Another one, the Rock Pro, has 5 cores at up to 1.8 gigahertz. Large RAM capacity. It's usual to see board with 2, 3, 4 gigabytes of RAM. Large storage, eMMC or SD card has plenty of resources. It's possible to connect display, etc. So this using this type of board to just resave and transmit, it's useless, and it's possible to add more processing and to have maybe the embedded board as a standalone device with a pre-processing or full processing, and for example with a cute plot to display a result. There is some small examples. The first one is Pluto SDR as a FM receiver with audio out, with a bit stream, modified bit stream to have a sound card, to integrate a sound card in the FPGA. So this board, in this configuration, the Pluto SDR receive FM modulation, do everything, and finally provide this to an ALSA sync, audio sync, without having the need to use an host computer. The host computer finally is only required to start the application and to configure the center frequency, and it's all. The demonstration is explained in the OSCIM digital repository in subdirectory tutorial Pluto S0, etc. And the corresponding BR2 external is available in again in the GitHub OSCIM. And another example is Raspberry Pi with big of resources with an RSRP B210 connected on with USB 3 interface, and GNSS SDR, the package, the application directly used on this board. This allows to have a standalone GNSS receiver. The GNSS SDR is not officially in a Buildroot. There is some prerequisite to fix before contribute this package. So currently it's available again in OSCIM underscore BR2 underscore external, and more precisely in the package as GNSS SDR. So now to have a second funny demonstration, we start directly. If you have a real board, it's possible to directly update your configuration. For QEMU, the first demonstration used as a virt machine, and without a device tree. The device tree is a description of the hardware. It provides the CPU type, the peripheral available or not, controller and peripheral. So it describes really the configuration of the board instead of a big file. It's a current, modern, and stable way to have this description. So for QEMU, it's required to move to another dev config. So it's required to rebuild everything. it's not required for this tutorial because binaries are provided to do the task, and the BuiltFruit configuration must be updated to with configuration previously applied in the first demonstration. But it's required to add the Qt5 because due to the complexity of this package, it's not possible to use only a select. So it's required to manually set this. Qt5 has no default font. So, for example, Liberation font must be set to have legend and every text on a Qt plot. And finally, it's required to enable the Qt GUI support in GNURadio. It's time to play again with BuiltFruit and with make menu config. Everything must be done in target package menu and font submenu to enable Liberation font. Next, graphic libraries and application to enable Qt. And finally, MISC to enable Qt GUI. Just a parenthesis, I've not mentioned this earlier, but it's possible to use Osmo SDR, to use DVB-T key, and it's possible to enable UHD to have access to USRP device. Since UHD, the library is has no complex dependencies, it's possible to use directly a select and to use this instead of having to enable the library before having access to this option. It's all. For configuration, it's all. Again, as mentioned earlier, GNURadio configuration has been updated, so it's required to use reconfigure to explicitly force BuiltFruit to apply all steps to this package, and finally make to build and to generate a new image. So now the QEMU command, some modification must be done in the command line because the VExpress board is based on 32 bits instead of 64. So we need to use system QEMU ARM. The virtual machine VIRT for this option is replaced by this one. To demonstrate, we use 2 core by using SMP, small RAM. This time we have a device tree, so we provide this file using this option. The root file system point to a real or emulated device instead of a virtual one. Since we want to use the display, we suppress the no graphic option, and we append with the serial with the stdio to have the prompt in the terminal, and we enable the VGA by using std. This time we need to use the package manager because the BuiltFruit version seems not to have a display support. And an important thing when we use Qt, there is many driver, many options to use frame buffer, OpenGL, etc. So we need to provide by a shell variable which driver to use. by using this command. So now I don't need, I've already built this. So we use this one to boot the new system. We have a new window with the display equivalent to a screen connected to the board. The number of tux is equal to the number of core in the for the specific board. So since SMP is equal to 2, we have 2 tux. Now a bit of GNURadio companion with a new project. For example, Qt demo. This time we have Qt on the board, on the emulator, so this option is left unchanged. We need to have a signal source again. Theoretically, it's possible to connect a USB key to the host computer and have access to the QEMU, but sometimes it's not really stable. Again, throttle. It's finally the same as the previous flow graph with a signal source instead of 0MQ, and finally a Qt sync. It's okay. Again, we need the Python script. And again, we need to use SCP. In my case, the board has already booted, so I don't need to drop the key. We have first this one not required. Bit of cleanup, a big file, root and root again. We need to use this one for Qt to move to TMP where there is a Qt demo, and to start this one by using this one. And after a bit of delay, the Qt sync must be displayed on the virtual screen, virtual display of QEMU. So now we have exactly the same display as previously with the 0MQ connection, with the time sync, the frequency sync with again a 1 kHz center frequency. So first we are able to use GNURadio and we are able to use an interface. Just a small conclusion about this tutorial. GNURadio is available in BuiltFruit build tools. It works on real embedded device or emulated, supporting ARM processor, RISC-V, PowerPC, MIPS, etc., or Intel architecture. Signal source and file source are not only solution. It's possible to use a UHD or Osmo SDR. And if you have this, Xterix device is available, not officially, but in a OSCIMP Bear2 external repository. And great thing with BuiltFruit is GNURadio, and everything is optimized for the targeted CPU instead of a generic CPU. Thanks.